use for elaborate references on this subject are listed here, a couple of them, but I will give the more elaborate list of references in the end of the talk. So in massless ABA, so we will restrict ourselves to the massless sector of this algebraic Bethe-Ansatz setup, and we are working in the specific background ADST times ST times T4 with pure Ramo-Ramo fluxes. So in this, the relevant algebra that we deal with is PSU 1/14. Once the ground state is fixed, then this is the remaining algebra. And there are 8 supercharges, basically labeled by the left moving, right moving nature. And so this algebra is tensor product of two PSU 1/1 squares centrally extended, and that is labeled by this L. So I labels the two copies of PSU 1/1 squares, and this capital I labels the charges in the single PSU 1/1 square, and they satisfy this nice commutation relations with the things in the RHS being the central elements. Furthermore, there exists a SU2 circle symmetry that comes from decompactifying this T4 to an R4, and that is useful to organize the spectrum that arises in the massless sector. Okay, so the representation that we work with, so now we have the algebra. Representations for the spin chain, putative spin chain, is a tensor product of two-dimensional representations of the component PSU 1/1 squares, and they are of the so these are the representations sitting here. So basically, one is a boson followed by a fermion, and here is the opposite. So fermion followed by a boson. There is a grading in this space, and we can tensor them to get a 4-dimensional space for the PSU 1/14. Now we can write down an R matrix for the PSU 1/14 as a graded tensor product of R matrices for the PSU 1/1 squares. And these components are like this, written in terms of spectral parameters in a very nice form. So this is a difference form result in the, so the entries are functions of difference of the spectral parameters, which hints at relativistic nature of these R matrices. And these variables are related to the usual momentum variables in this sense. Now that we have the R matrix, we can write down a monodromy matrix by again tensoring the component monodromy matrices of the PSU 1/1 squares. And we can write them in the auxiliary space as operators on the spin chain like this. And so tensoring these two, we get the PSU 1/14 monodromy. And the transfer matrix is the supertrace over the auxiliary space of this monodromy matrix. Now, if we define B operators of this type, so these are just the B operators of the PSU 1/1 squares, then what turns out is we can write down a Bethe state of this type, where this is the ground state, pseudo vacuum, with some impurities labels attached to them. So with this Bethe state, now if we impose certain algebraic conditions on these parameters sitting inside the B operators, what happens is this state turns out to be the eigenstate of the transfer matrix. And so this exhausts all the eigenstates that that one gets from the transfer matrix brute force diagonalization. So that was the algebraic Bethe-Ansatz setup. What turns out is if we restrict to zero momentum limit of the Bethe states, then that corresponds to, first of all, gamma I, the impurities at the sites going to -infinity, and restrict to fermionic modes only, then the states that we get correspond to protected multiplets of the theory. Why? Because they are annihilated by the PSU 1/14 centrally extended algebra. Now, if we need to write down all the protected multiplets, we need to include this SU2 circle symmetry, and that gives us extra level on the massless basis that we had written previously. And furthermore, what we see is that if doing this procedure of taking the zero momentum limit, we get states only at the very low lying frame particle cases, which is 0, 1, 2, 3, or 4. And listing all of them out, we get recover the Hodge diamond for 4 torus. which is like this. That's nice. Now we can take an orbifold of the 4 torus, and so the specific orbifolds that we are concerned with are this n gamma equals Zn, where n is equal to either 2, 3, 4, or 6, and this correspond to cases where the resolution of the T4 after the orbifold action turns out to be a K3. And in these cases, what happens is the gamma group actually just acts non-trivially on the C2 circle index that I mentioned earlier, and in this specific manner. So if G is the generator of the Zn, then the action is of this type on the fermionic modes of the Bethe state. So, so we have the action, and we can then write down the Bethe states that are invariant under the orbifold action. It turns out that for n greater than or equal to 2 in this gamma equals Zn, these are the orbifold invariant states. For n equals to, there is a further enhancement because G squares to 1, and we get a bigger set of invariant states in the untwisted sector. For twisted sectors, we need to, so this is part of the story, right? For orbifolds, we need to consider the twisted and untwisted sectors. In the twisted sectors, we need to modify the Bethe equations by including a twist angle of this type. Bethe equations specifically at level 0, one of the Bethe equations that I had previously listed. And if we take the 0 momentum limit, what happens is only the ground state survives. None of the fermionic modes, higher level Bethe states can survive in the 0 momentum limit. So we just get one state for each of the twisted sectors. So we further generalize the results to mixed flux case by including the analysis in terms of a different set of variables for the R matrices known as Zhukovskys. So finally, I would like to list some of the future directions that we are thinking about right now. So protective states that we have listed, we discuss it in the ABA. However, we need to consider the thermodynamic Bethe answers in massless TBA. So in order to make statements that are, in order to be confident about our results because of Lucia corrections that might keep in. And yeah, so basically once we have the TBA, we can then make statements about the wrapping. However, there are strong hints that the wrapping corrections won't affect our analysis. Okay, so that's it. Yeah, and some references for people.
Okay, thank you very much. I think that Alessandro disconnected. Maybe. Okay.
Yeah, I don't see him. Yeah.
Okay, yeah, I don't see him. But okay. Well, thank you very much for your talk. Are there any questions or observations? Okay, sorry. Alessandro is back now, I think. Let's see. I guess. Sorry for this technical issue. Alessandro, you.
I'm now back, and I apologize, but my internet just crashed, so I missed the last part of the talk. I'm really embarrassed. So I might have some questions about your talk, but given that I missed the talk, maybe somebody else will ask more intelligent questions first. Okay, then maybe I will have a non-intelligent question, and I apologize if this was already discussed in the talk. In order to see that a state is really protected, you want also to account for finite volume corrections. So
yes,
do you have any comment?
Yeah, so that's actually, so we need the TBA for that, right? We need the mirror TBA for analysis for that.
Yes and no. Also, I would disagree with the fact that you can just use the massless TBA as you've written there, because in order to construct a TBA, you really need the whole TBA in order to have a proof. But in the case of T4, this could be done just by observing that the S matrix was such that order by order, the transfer matrix was such that order by order wrapping corrections would cancel between bosons and fermions when the physical particle was at p equals 0. So do you have a similar statement here, perhaps?
No, that's the kind of work that we are trying to, that we are thinking about right now. So for the orbifolds and the mixed flux backgrounds, basically, how to make such arguments. So yeah, that's the thing that we are currently thinking about.
Okay, maybe during the longer break, I'd be very interested to discuss this.
Yeah.
Are there any further questions on the talk?
I just want to present this result that we, that is the highlight basically, that we recovered the nice K3 Hodge diamonds for the single analysis. Okay. If not, I guess.
Maybe a quick one. Do you have anything to say about the non-orbifold K3?
No. The construction completely hinges on that. It can be realized as a T4 orbifold.
Okay, then I would thank you very much for the talk. And again, I apologize for missing part of it.
We can discuss later.